The theme of the 9th lecture is magnetic field. From this lecture, you will learn what is magnetic field, what are the properties of a magnetic field, principle of superposition for a magnetic field, Biot-Savart-Laplace law, a force acting on a current-carrying conductor, and the interaction of currents. To understand this lecture, you will need the following vocabulary: current-carrying loop, контур с током, positive normal, положительная нормаль, left-hand rule, правило левой руки, infinitesimal segments, бесконечно малый отрезок, circumference of the loop, периметр контура, infinite straight current-carrying wire, бесконечно длинный прямой проводник с током, a finite straight wire, прямой проводник конечной длины, homogeneous isotropic medium, однородная изотропная среда, right screw rule, правило правого буравчика, torque, вращающий момент. In 1820s, Ørsted discovered that electric current produces a magnetic field in the space around itself. This discovery gave the birth to numerous studies of the magnetic field. Many experiments have shown that just as charged objects produce an electric field in space around themselves, the same way bar magnets and current-carrying conductors produce a magnetic field around themselves. In this picture, we see a bar magnet, and around this bar magnet, we see the electric field lines, which show the magnetic field distribution around the bar magnet. We see that magnetic field lines, they emerge from the North Pole and enter or end at the South Pole. The same for a current-carrying conductor, around this conductor, there are electric field lines which also show the distribution of the magnetic field around a straight conductor. So we see that there are magnetic fields around the current-carrying conductor or bar magnets. So two experimental facts were established about the magnetic field. First, the magnetic field acts only on moving charges. The second, only moving charges produce a magnetic field. So if to place the magnetic needle or any current-carrying loop in the magnetic field, it can be noticed that they turn in the field in a certain way. The magnetic field exerts on the needle and current-carrying loop orienting effect, turning them in the direction of the magnetic field. Orientation of the loop in space is characterized by the direction of the normal to a loop. A normal is called positive if its direction is associated with that of the current in the loop by the right-hand screw rule. EDS, the direction of progress of the right screw, determines the direction of a positive normal if the head of the right screw rotates in the direction of the current in a loop. The fourth characteristic of a magnetic field is the magnetic induction. Its magnitude is defined as the ratio of the magnetic maximum torque acting on the loop to the magnetic moment of the current-carrying loop. That is the magnetic moment of a current-carrying loop, where I is the current through the loop and the S is the area enclosed by this loop. When the positive normal to the loop is in the direction of the magnetic field. So the magnetic induction is determined by the ratio of the maximum torque M maximum to the magnetic moment of the current carrying loop. The magnetic field is visualized by magnetic field lines, as I said. The direction of magnetic field is tangent to the magnetic field lines at any point in the space. And you see here that the magnetic fields of the field lines of a straight current carrying conductor, and they have no beginning and ending, and they are continuous, and they never cross with each other. And we see that at each point of this line, the magnetic field is tangent to the lines at this point. The principle of superposition for a magnetic field states the resultant field set up by several currents equal to the vector sum of the magnetic field set up by each current separately. So here in this picture we have three currents, and the cross in the picture shows that the current's direction is into the screen. So here we have three currents, and all of them have direction into the screen. And we find the magnetic field produced by each current at the point P. And this magnetic field B is equal to the vector sum of magnetic fields produced by the first current, by the second current, and by the third current. So it is, we can write here that B is equal to B1 plus B2 plus B3. The force exerted on a straight current carrying conductor in a uniform magnetic field is equal to this expression. So the force, for example, if you have a current carrying conductor, current in this direction, and if you place it in a magnetic field, for example B, then this will be the angle between them, alpha, between the direction of the current and the magnetic field. In this case, a force equal to the vector product of the length of the current to the magnetic field will act on this current carrying conductor. Here I is the current through the conductor, L is the length of the conductor, and B is the magnetic field. The direction of the force is determined by the left-hand rule. So for this, you take your left hand and direct it in the direction of the current. So you hold your left hand so that the four fingers of your left hand will direct in the current, so that the magnetic field lines will enter the palm of your left hand. Then the erect thumb will show you the direction of force on a current carrying conductor. The numerical value of the magnetic constant is found from the fact that two parallel conductors being 1 meter apart from each other and carrying current of 1 ampere interact with the force which is equal to 2 times 10 to minus 7th power Newton per meter. And the substitution of these quantities into this expression gives us or allows us to obtain the numerical value of the magnetic constant. And it is equal to 4 pi times 10 to minus 7th power Henry per meter. So let us make the summary of our lecture. Magnetic field is a kind of matter that exists around permanent magnets, current-carrying conductors. Only moving charges produce a magnetic field. Magnetic field acts only on moving charges. Magnetic field exerts on the needle and current loop orienting effect, turning them in the direction of the magnetic field. Magnetic induction is the force characteristic of a magnetic field. It is defined as the ratio of the magnetic torque acting on a loop to the magnetic moment of the current carrying loop. That is the magnetic moment of the current carrying loop. The direction of the magnetic field is tangent to the field line at any point in space. Magnetic field lines can never cross, and they are continuous, forming closed loops without beginning and end. The principle of superposition is true for magnetic field. So the magnetic field, due to several currents, is equal to the vector sum of the magnetic fields produced by each current. Biot-Savart-Laplace law determined by this formula, and it gives the magnetic field produced by the element of a conductor, dl, which is carrying the current I at the distance r from this element of the conductor. Magnetic force on a current-carrying conductor is defined by this formula. It is directly proportional to the current flowing through the conductor, directly proportional to the length of the conductor and to the electric field. Magnetic constant is defined from the interaction of two parallel conductors, and it is defined to be equal to 4 pi times 10 to minus 7th power Henry per meter. The lecture is over. Thank you for your attention.